I'm going to talk about how we can use satellite measurements to look at unrest and volcanic eruptions. And I want to start off, how can I change slides? Like that. By saying that I think there's two angles that people can take to this problem. So one is making measurements of volcanoes to try and advance our fundamental understanding of magmatic processes and volcanoes' roles in planetary systems. And the other approach is to try and work out how we can better monitor them in a practical sense. And I guess I wanted to start off by saying is that I'm interested and motivated by both of those applications, and I think that they feed back and forth to each other. I think some of the best science comes from trying to solve monitoring problems, and sometimes the advances that you need for monitoring come from pure science. So there's a bit of back and forth. And the other thing I'd like to say as a preface is I'm going to present bits and pieces of work from various PhD students as I go. This is their wall of faces. I'm going to try and call them out on the way as I go. And it's a privilege to be able to work with lots of bright students and early career researchers to put this together. So the way I've organized this presentation is I'm going to start off talking about what the critical data sets are for volcano remote sensing and for monitoring, and why I think they're particularly, why I think they fill a gap, they fill a niche, and they have a role to play for monitoring systems. And then I'm going to give you 3 scientific questions. So the brief for this seminar asked for what the scientific questions in the field are, and I struggled with that a little bit because I had long lists of things I thought I could talk about. So I've come up with 3 fairly subjective questions that I'll expand on a little bit. But I'm sure you could all add a lot more to what I've got here. And then I'm going to go through some themes in satellite remote sensing of volcanoes and future research directions. So quite a lot of those themes have already come up in this morning's discussion. So it's how to deal with big data sets, how to deal with machine learning, what we can get from machine learning, what we can't, and the challenges of monitoring and modeling magmatic systems in a way that's kind of productive and gives us information that's useful. And I'm going to go on to talk about 2 particular case studies. So one is detection of critical transitions and a fusion rate at Soufrière St. Vincent. And the other is an integrated look at Sentinel-1 time series from the Galapagos Islands. So first of all, right back to basics. I think there are probably the most important data set for monitoring around the world, arguably, is still seismicity. And that's great, and it's normally the fundamental basis for monitoring at volcanoes where there's good monitoring infrastructure. But where there isn't any infrastructure, and where volcanoes aren't monitored, and I think there's a lot of volcanoes which are potentially active around the world that still have almost no ground-based monitoring network or insufficient monitoring network, I think satellite remote sensing has a major role to play. And there's 4 kind of main parameters that we can currently get. I think 4 that are widely measured, say. So one is deformation and INSAR, and that's my particular area, and I'm going to dig into that a lot more deeply in the rest of the seminar. But the others are retrievals of ash, retrievals of SO2 and some other gas species, but primarily SO2, and measurements of thermal emissions, so temperature anomalies. And you can see they're using different parts of the remote sensing spectrum. But the kind of fundamental basic point to make about radar versus optical IR, shortwave infrared, near infrared, is that we can make radar measurements through clouds, and we can make them at any time of day, so it's potentially quite a stable data set relative to optical retrievals. So the other point about deformation measurements from space is that they are, on average, more likely to occur in pre-eruptive periods than thermal emissions and gas emissions, and that's primarily because the big sort of gas emissions that are easily detectable tend to happen during eruptions or when the volcano is already quite active. If you look at given time windows, the presence of a deformation signal, no matter what that deformation signal originates in, whether it's hydrothermal, magmatic, something to do with the structural process at the volcano, is a good predictor statistically of there being an eruption within the same time window. And that's something we've tested with 3-year windows, with 6-year windows. And most critically, you can link deformation measurements to physical models that allow you to locate and track and potentially even forecast the movement of magma through the crust. But these measurements aren't evenly distributed, so that the global maps that I'm showing there are for, you've got deformation measurements, thermal measurements, and SO2 from all different sensors. They're all kind of mixed up. So this is volcanoes at which positive identifications have been made around the world. On the right, the figure shows, I've got something along the x-axis there, which is number of Class A volcanoes. So this categorization comes from a USGS scientific investigations report from 2022. And part of the effort with that work was to look at volcanoes around the world and assess what the needs for satellite remote sensing were. So we did that on several bases. So one was looking at the population exposure index around the volcano. One was looking at the level of activity at the volcano, and the other was indicators for unrest. So we came up with a set of categories. But essentially, A1, those are volcanoes that are either erupting, have erupted recently, and they're also near large centers of population. So they're what we think should be the priorities for monitoring. So we might expect there to be similar detections, given these are all similarly active volcanoes, in proportion to the number of volcanoes in a country or in a region. But that's not actually what you see. You've got a kind of general trend there going up, and there are some significant offsets to that. So the main one that I'd like to draw your attention to is actually Indonesia. You see this green dot. You can see my mouse. The green dot down here shows here's the number of deformation measurements that have been made in Indonesia, and this was about in 2020. And you can see it's way lower than one would expect, given the number of extremely dangerous volcanoes. And there are good reasons for that related to the challenges of making measurements in densely vegetated areas, but also into the resource that's been applied to the problem. And you can see a couple of other anomalies also in tropical regions, Australia, Melanesia, and Central America and Mexico. There's also a difference in what information parameters you can get from satellite data sets depending on where you are in an eruption cycle. So in the visible infrared and retrieval of gas and ash sort of realm, that's mostly looking at things that have happened after an eruption has started. Passive degassing can be measured, but it's much more challenging, and it requires a significant gas flux to get good retrievals, or at least in historical data sets it did. I think things are much better now. But with INSAR, you have some possibility of getting pre-eruptive signals, not at every eruption, but for some significant proportion. So I'm going to give a little bit of very basic background to satellite radar detection of deformation. It's definitely too basic for a lot of people, but hopefully it kind of gives a context for anyone who's not worked with a data set before. So displacement isn't the only sort of parameter you can retrieve from satellite radar. If you take individual images, you can look at the proportion of energy which is scattered back to the satellite, the backscatter or the amplitude, and you can use that to look at changes in the surface roughness of the ground, changes in local slope, and retrieve something about what's been erupted. If you want to look at the stability of the phase, you can also use that to map out any surface changes. And finally, you can retrieve topographic change if you have the right geometry of image acquisitions. So if you have images which are taken from sufficiently separate perpendicular baseline, you can retrieve from the phase a change in elevation on the scale of meters. But primarily what people use it for, and the most kind of powerful tool, is to retrieve deformation of the Earth's surface on the scale of millimeters to centimeters. So these are classic slides. They're so classic I can't actually remember who made the figures, but they've been passed from person to person, they've been inherited, so I'm not crediting them properly. But they're classic for a reason. If you want to make a measurement with interferometry, it's essentially a matter of working out what the phase shift is between the ground at one time and the ground at another time. And that requires an image which is taken from more or less the same location. And it requires a set of corrections to remove the other contributions from the phase that look like a phase shift. So when the satellite returns to one position and then moves to the other, you have a shift in the phase which is offset something like that. And what that looks like in practice is two complex images, which if you like, you can separate into amplitude and phase. The amplitude looks like a grayscale image of the Earth's surface with some distortion because of the side-looking viewing geometry. And the phase looks essentially like white noise. And this is one of the most fun labs to teach undergraduates, because when you get to make an interferogram, you look like you take noise, add it to noise, and get signal, which was like some sort of magic. And you get a beautiful pattern of fringes, which you can then interpret. So an analogy for explaining how this works, you could say that if you were counting the number of ripples across a pond and you knew the distance between the ripples, you could use that to estimate what the distance across the pond is. So using an earthquake example here, you can count out along the fringes. And this process of unwrapping or integrating across the phase field is one of the more challenging things in interferometry. And in volcanic cases, essentially what we're trying to do is take multiple maps of displacement, of contour displacement represented by these fringes, preferably with multiple viewing geometries, and use that to unpick what the source geometry and volume change is of a change in the subsurface. And that's the aim after a lot of correction and a lot of work, and use that to try and understand something about the volcanic system. So my three subjective questions are, so how can we use these sort of geophysical parameters to forecast eruption onset and eruption duration once an eruption's already started? What's the nature of magma storage in the crust? Can we retrieve its properties from satellite-based geophysical measurements? And finally, I think one that's kind of increasingly important and increasingly accessible using satellite data, what's the impact that volcanism has on the surrounding environment? So with this first one, I think you can refine this question a little bit to say, can we anticipate transitions from unrest to eruption and from effusion to explosion? And unrest to eruption is a slightly more subtle problem because the changes that take place to trigger an eruption are potentially very small and potentially happen a long way from where we can make measurements that are relevant. So I think the most important thing in that case is to have time series of of regular images that you can interpret change and identify change. And then the related one is whether you should be trying to use physical models and understand what's happening in a volcanic system, or whether a more profitable avenue is to use kind of time series or anomaly detection. And I think there's a place for both approaches, and it's obviously most powerful if you can bring the two together. So I'm going to come back to this questions of transition and eruption style with a St. Vincent case study. So what's the nature of magma storage in the crust? So historically, there's a lot of work that has been done, and some of it quite well matched by observations that come from data, where people assume that you've got a chamber which is filled with liquid, which inflates before an eruption, deflates during an eruption, gradually cools, and then inflates before the eruption again. And there are some volcanoes around the world where you see something like that. But as soon as you actually start looking at data, of course, it's a lot more complicated and a lot richer process than this. The only example that I have studied personally myself that has such a perfect classic eruption cycle is Wolf in the Galapagos, where the gap between the 2015 eruption and the 2022 eruption just showed a beautiful constant inflation the whole time, undisturbed by all that much else. Although we'll come back to this time series later as well, because I think there's actually a little bit more going on here. Just to give you some ideas of the complexity in the volcanic eruption cycle that aren't captured by that simple model, we actually know that pulses of melt recharge reservoirs. Santorini being a nice example, like not even thinking about the current unrest, there was this pulse of uplift back in 2012 and 2011, which was actually measured with deformation then. And we know similar events had happened throughout its history without necessarily resulting in an eruption. Regional stresses dominate magma movement in many settings, so that we're not just talking about magma moving within a reservoir straight up to the site of eruption, but actually entering the crust and traveling through the crust at great distances determined by regional stress fields. And the links between eruption feeding reservoirs and stored magma are complex. They're not quite as simple as you would think if you were only looking for a reservoir directly underneath a volcano. So to give you an example of a non-classic eruption cycle, I want to show this is Sangay volcano in Ecuador. Sangay is the most frequently erupting volcano in the country. It sits right on the edge of the Amazon basin. It's relatively poorly monitored because there aren't dense centers of population around there. Occasionally ash from Sangay does affect things in Quito, but it's not got a dense instrumented network like other volcanoes in the country do. And this work is by Pedro Espin-Bedon, who is a staff member at Instituto Geofísico Quito, and also has just finished just about to submit, probably next week, his PhD in Leeds. And with Pedro, we spent a long time really trying to understand what was going on in the deformation at Sangay. And you can see there, the data is kind of horrible because it's surrounded by dense vegetation. You've got a very limited range of coherence. You have frequent eruptions, which were in the coherence at the summit. It's a tricky data set to work on. And more than that, because of the way that we had done the processing initially, you had a kind of long-term fading bias in the signals because we used short-term 12-day interferograms. So we spent a long time trying to convince ourselves whether this apparent uplift, which goes from 2016 up to date really, was real or was an artifact of the data being unreliable. And eventually we developed a new network construction. You can see, I want to show on this figure here, that this spans a period of particularly active activity at Sangay, where you had more explosive eruptions and you had more kind of energetic pyroclastic flows than you'd had before. And the really interesting thing about these time series is that you can see this long-term trend in uplift, which is kind of centered beneath the western flank of the volcano, is modified by several of the explosive events. And it's difficult for us to make sense of the deformation during those events itself, but the time series analysis really picks up systematic offsets during the explosions. And what we see at Sangay is not so much that you get a refilling of the reservoir in between eruptions after complete emptying, but a continual accumulation of magma within the volcano's edifice in spite of the eruptions going on. So we tried to model this, so that's represented by this time series here. You have a kind of relatively constant uplift rate or steady uplift rate through time, modified by small eruptions, and the eruptive flux is small relative to the flux that's intruded into the volcano. So we modeled that using Valerie Cail's DEF-VOLC approach, using boundary element modeling, so that we could do justice to the topography of Sangay, which makes taking a simpler approach and making simplifications with topography less reliable. And what we found from that is that a range of sources can more or less fit this, but you've got a challenge in that you have an apparent uplift in the ascending track not matched by any sort of signal in the descending. So you really have to have some kind of inclined source. And because we've kind of modeled this over the whole time period of uplift, it's difficult to pull apart whether this source is kind of consistently active the whole time, or whether actually what we're seeing is the sum of magma movement on a shape with this sort of axis, with some more subtleties in its movement. So going back to the simple modeling, the next question is that chambers themselves probably don't give us a full picture of what's going on in the Earth's surface. There's a much more kind of widely accepted idea now that in fact magma reservoirs are surrounded by cooler crystal mush, and the lenses of eruptible melt, are not necessarily kind of extensive or connected together. And connecting that idea to deformation is challenging because it completely modifies any volumes that we get from inverting deformation data. And it also would have a dampening effect on pressure changes in the subsurface, which would make them harder to detect geodetically. So you can add kind of as much complexity to this problem as you like. You can go from something that's elastic to elastic with some topography and structure added in. You can add in viscoelastic properties to the crust. You can make choices of whether you expect viscoelastic properties to extend mostly below the reservoir or to encompass it in a shell, and all of this produces kind of differences in the scale of and the pattern of the deformation that you get at the surface. More than that, you really need to think about magma compressibility if you have magma stored at a depth or you have bubbles. So all of these things are things that we know to be the case and are likely to affect magma deformation, but they tend to be poorly constrained, and we can't necessarily capture all of this complexity in every model. So I think there's a question, almost in all cases, as to how far we go down this kind of tree of complexity. And recent work by a couple of different groups have tried to address poroviscoelastic reservoirs. So that's where you have a poroelastic behavior within a reservoir itself. You have viscoelastic behavior within the matrix of the mush that surrounds it, and that gives you an additional modification. And it's difficult to model. You can do it in a kind of numerical approach, like using COMSOL, and there are a couple of analytical solutions that you can use, but they're highly dependent on your boundary conditions, and they're highly dependent on the way that you start up the model, what kind of source function you use for the injection. So I'm going to leave that one and we'll come back to modeling a little bit later. The third question that I think is kind of interesting and increasingly accessible to satellite data is the impact that volcanoes have on the surrounding environment. And that's something that's pretty diverse. You have very explosive eruptions that can send material up into the stratosphere and have large radiative impacts. The figure on the left here shows radiative impact of passive degassing, kind of tropospheric effects. This is downwind of Kilauea, of Reunion. This is a very old figure, but it shows how cloud effective radius is modified downwind of Reunion during explosive eruptions relative to periods of relative quiet. But the better our retrievals of atmospheric properties, of cloud properties, and so on, the more that we can pick out of these volcanic impacts. And I think that's something that with the new, more kind of atmospherically inclined Sentinel missions and other ESA missions that are going to be launched in the next few years, we'll be able to do a lot better with than we have in the past. Another angle of this is looking at the impact of volcanic eruptions on surrounding vegetation and plant life. So this is work from Megan Udy, who's also due to submit her thesis fairly soon. She's looking at the impact that various volcanic eruption outputs, so ash, SO2 emission, flows in channels, have on vegetation. And this is one of those observations that's been made kind of very widely by a lot of observatory scientists and a lot of people who work in the field on volcanoes, but it's not something that people have systematically studied in very many places. So she's using satellite retrievals of NDVI, so essentially how green plant life is, as well as different polarizations of radar data to assess the health of vegetation immediately after an eruption, and particularly looking at how long it takes various ecosystems to recover from volcanic inundation. So this example on the bottom right here is from Calbuco. I'm sure a lot of people are familiar with this eruption. The map on the left shows, I think, the week before the eruption, and this is what it looked like afterwards, with the red colors being vegetation that's destroyed. And you can see these transect figures with the timeline going down show how quickly the recovery takes place in distal areas and how long it takes further in. And there's some interesting complexities to that signal of recovery, because sometimes you find that areas a little bit close to the volcano recover better than areas further away that don't have frequent inundation and don't have stands of species that are resilient to volcanic impacts. The nice thing that Megan was also able to do with this was to improve retrievals of ash isopaths by looking at the change to the vegetation relative to measurement points and using that to aid a different interpolation. So she was able to refine the maps that had been placed by other people by essentially doing a calibration against the remote sensing data. I'm showing you this example just for fun because other people have mentioned Krakatoa today, and this is evidence of an impact of an SO2 from Krakatoa on one of the surrounding islands. In spite of quite frequent eruptions, the vegetation on the islands around Krakatoa are not routinely affected by activity, except when it's very large. But in this particular case, an SO2 plume with relatively low wind speed touched ground on this island and damaged the vegetation extensively. And you can see that as a drop in the greenness, which kind of recovered relatively quickly. Okay, so I think we've got another half hour. So I'm going to talk fairly quickly through some big themes in volcano remote sensing and then go on to the case studies. So the first one is big data and automation. And the example I have, apologies, this isn't a volcanic or even a geophysical example, but it is quite big data and it involves sentinel data, which I think is widely used in tectonics. This is a map of wetland location in Africa, which one of my students put together using a kind of integrated classification based on Sentinel-1 radar and Sentinel-2 optical imagery, essentially to separate out types of wetland like mangroves from swamp, from shallow lakes, and so on. On the left there, you can see this study, so that's showing you the resolution and kind of what you can attain with the current satellite imagery. And the two maps on the right come from various kind of land surface classification data sets, but that's the previous resolution. And you can see the sort of questions you can ask with the high resolution data are completely different. And in fact, what Sani's managed to do is look at the links between fragmentation and distance to population, and dense population, so population index across the whole of Africa to identify particularly vulnerable bits of wetland. So I show you this in spite of it not being normally the sort of thing a geophysics institute might deal with, essentially because I think it's a nice illustration of the advances and the possibility of answering new questions given high resolution global data sets like this. And cloud computing power, for that matter. So this figure shows the kind of burgeoning of satellite radar data availability since the 90s, and it shows the diversity of wavelengths. So red is L-band there, about kind of 20 centimeters. Green is C-band, and X-band is in blue. And it's the sort of work that you can do with that multitude of wavelengths is a little bit more. You can ask more specific, more nuanced questions, particularly when you're using backscatter, because you're capturing different processes. So one of the big initiatives at Leeds, where I'm based at the moment, we're led by quite a large group of INSAR scientists, but people who are associated with COMET, is the automated processing analysis of Sentinel-1 imagery, and we've put a lot of kind of effort into this over the last decade. It's essentially trying to process all of the data across the whole Alpine Himalayan belt, most tectonically active regions of the world, and most places where there are active volcanoes. And its automated data processing involves making a lot of choices and deciding for what purpose you optimize the automated processing. And it's kind of a continual development. But we've got many tens of thousands of interferograms that are kind of served over the internet, and we can use them to ask quite a lot of questions that were not accessible before. So this is an example from Jess Payne, who's another PhD student in Leeds. She's produced the velocity field along with previous students, including Andrew Watson, to look at the tectonics of Iran. But actually the most dominant signals there are basin subsidence. And the countrywide assessment that she's been able to make has included looking at strain accumulation with impacts for hazard, but also looking at whether or not this deformation is likely to be related to kind of inelastic or elastic processes within the reservoir, and whether the reservoirs will be permanently impacted. So another big theme, which I think is true for all geophysics research, no surprise for anyone, is the application of machine learning. So you can do that in a few different ways within SAR data. We can look at supervised processes, detection, classification, noise reduction, and this has been done for interferograms with kind of convolutional neural networks, with anomaly detection processes using kind of variational autoencoders. So the example on the right here is from Anza Shakil, and she trained data on southern Turkey, essentially just on the structure of INSAR data, so not supervised classification here, just learning the structure of the data when no signals were present, and from that she was able to flag any interferogram that had deformation in it. And that included, for example, this volcanic signal, which is Demuyu. And the alternative approach, or one of the alternative approaches, is to deal with things in an unsupervised way. So separate signals out and use that for change detection. So this is work from Matt Gaddis in Leeds, where he's done an independent component analysis decomposition of an INSAR data set. And he's identified one component which is likely to be a volcanic signal, as opposed to the others, which we think are mostly atmospheric. And he can assess the strength of it at different times, and that forms the basis of a detection algorithm for when activity at a volcano changes in terms of deformation. So coming back to Jess's example, she used ICA, a similar method, to separate out inelastic deformation, which you'd expect to be linear, from elastic deformation, which you'd expect to have some sort of kind of seasonal pattern to it. And from that, she can map out more or less where in Iran there's been permanent loss to aquifer capacity, and where there's going to be decreasing supplies for irrigation in the future. So because we're a data-driven field, the other thing that I think drives the science forward are major events that take place every, on a decadal scale. I mean, in the last few years, I think Mayotte is one example. The other is the Reykjanes fires starting up again. We have continual new dike injections and eruptions taking place in southeast Iceland. And I think from these, we normally learn something new because it's a new observation that hasn't been possible before. Another one that I think has been important in the last 10 years is the flank collapse of Krakatau, which, although it wasn't detected from satellite in advance of it happening, retrospective analysis by various groups have shown that the slope of the flank that eventually collapsed was moving at meters per year for quite a long time before. So I think it's a driver for monitoring targets. So one of the considerations with satellite data is, although it allows us to see a lot, and we can see a lot over a really large area, there are limits to what it allows us to detect. So I think one of its powers is that it allows us to look over large areas in a kind of systematic, unbiased way. So from that, I think one of the important observations we've made is that deformation, although it tends to be centered on active volcanic systems, quite often extends quite a long way away from the volcanic edifice, sometimes tens of kilometers, sometimes 25 kilometers. So these histograms here and the sketch is essentially to scale. You can capture most volcanic deformation signals if you go to a diameter about 20 kilometers on either side of it. But then you still have some which are not necessarily associated with surface features. So that's useful from a monitoring point of view because it tells us like how large our patch size that we need to process is. But I think it also tells us something about the kind of catchment area for magma that underlies volcanic systems. But what we miss are processes lasting less than a few days, changes that happen between acquisitions taking place, and also sometimes low-rate long-term processes. And resolving the timing events is still a challenge. So this example is from Socompa in Chile. So this is a volcano which has no historical record of activity at all. It wasn't monitored. There's a GPS base station not that far from it because people thought there was nothing going on in the area. But when Fei Liu, who's a PhD student at Leeds as well, he was actually interested not in volcanoes at all. He was a tectonics person. He was looking for a deep earthquake near Socompa. And when he looked at the interferograms, he actually found that Socompa started uplifting the same year that this relatively deep earthquake took place. And we spent a long time trying to resolve the timing of the two events. It looks like the uplift started before the earthquake, but it's a challenge to pull these things apart, given the temporal resolution of the INSAR data. And he's done a compound dislocation model of the best fit source of the Socompa uplift, and he finds a kind of mid-crustal depth, which is actually relatively shallow compared to some of the Atacama volcanoes. Okay, so I'm going to move on to some of the case study examples now. We still have some time. So this work came from Edna Douala's PhD. She's worked extensively on how to get the most out of radar amplitude for remote sensing, so looking at backscatter. And what this work that I'm going to present here particularly focuses on is retrieving a fusion rate for an ongoing eruption at St. Vincent in the Caribbean. So fusion rate is a critical parameter if you want to forecast the duration of eruption. But it's quite difficult to measure because it requires someone being there in situ. It requires kind of clean line of sight for getting photographs of the dome growing, for example. So these are TerraSAR X images that span a period of dome growth at St. Vincent, January to April 2021. You can see it kind of growing there around the older pre-existing dome within the crater. And eventually, at the end of this period of dome growth, there was a major explosion, which was very destructive. It made a completely new crater topography. And this was, to give you a flavor, this was a really fast-growing event. So these two animations here show one-day acquisition pairs, and that's something that we still don't routinely get, but it happens occasionally with a constellation of Cosmos SkyMed instruments from the Italian Space Agency, because they have 4 satellites, and occasionally you get one-day separation with a good baseline, and that's what we have here. And you can see this was early in the dome's growth, and the one at the bottom was late. And you can see this massive bulge in the center of the dome, which was just before the whole thing went. So it was quite serendipitous timing in terms of the image acquisition. We were lucky to capture that. So there were 3.5 months of dome growth, sudden transition from effusive to explosive, and it's a relatively small data set of images that I'm presenting, but they're from different wavelengths. There's 2 X-band and 1 C-band instruments. And the assumption that underlies this work is that the backscatter is dominated by a change in slope gradient, so that we can use the backscatter information to retrieve the topography. It's quite a big assumption, but in this case it works relatively well because the change in slope is definitely the largest change. We kind of justified that assumption to ourselves by saying that we expected the material that the new dome was made of to be similar to what the older dome was made of on the wavelength of the radar, which is what we're sensitive to. So the way that Edna analyzed this is that she basically went along range lines and integrated along those lines to try and solve for what the topographic change would have to be in order to match the backscatter that we saw. It's a pretty noisy thing, it's a non-unique solution, so you also have to add in some other constraints. So she did some smoothing based on a triangular mesh, and that did a reasonable job of giving topography that was plausible for the dome, given we roughly know the shape of it. There are a couple of assumptions you have to make about crossing zones of shadow and about foreshortening, where you get distortions due to the geometry of the side-looking radar. And the background DEM that she used to do all of this was Pléiade derived, made by Raphael. So you can see that this red line here is the new dome. The black line is the pre-existing topography with the old dome up here, which you see we've not matched perfectly in that particular retrieval. And this is the interpolated dome from the triangular mesh. And these are her results at different time steps. So kind of right at the beginning, halfway through the eruption, and shortly before the transition to an explosive event. And what's really cool about this is that the timing of the acquisitions meant that we actually were able to make an estimation of a fusion rate. And this was something that was being done in any case by the observatory by structure from motion measurements. But what the satellite data added in retrospect, we didn't do this at the time, this was reanalyzing the data later on, was temporal sampling that kind of doubled the number of images that you could, the number of dates at which you could get a new topographic elevation model. And in particular, we had that one image pair that captured the days just before the eruption. And what we saw was that the rate of exfusion was relatively constant. It was pretty steady through this whole period here. And then right before the eruption, that's this inset up here, we had an increase in rate of almost an order of magnitude. And that kind of gives you some indication that this was explosion was a bottom-up led event rather than triggered by the collapse of the dome at the surface. And actually that is consistent with what was retrieved from the tropomi measurements, which was a very small indication of some degassing which started before the eruption actually took place. So this would be a really nice study to try and replicate in other places, but it requires serendipitous acquisition of imagery. And more than that, if you want to have that one-day pair and those kind of short acquisition times, you have to combine multiple different sensors to get it. So it's kind of an argument for non-uniform data and for more data. So moving to a completely different case study. This is the Galapagos Islands. And if I go back to my original sketch, this work aimed at getting at the deeper parts of the volcanic systems. As you know, if you've made any deformation measurements over islands, it's frustrating because you only really get the shallowest part of the system up to the diameter of the island itself. So looking at what's going on deeper is not something that you can access by direct measurement with deformation. But the idea here in Owen's PhD was to look at multiple deformation signals from across the Galapagos and try and understand the link between them. The Galapagos is a perfect place to do this because it has incredibly high rates of eruption and it has beautiful large deformation signals associated with most of what's going on there. I think a lot of the things that complicate analyzing deformation don't apply in the Galapagos. You don't have kind of large stress fields surrounding the reservoirs that kind of control things. You have relatively small distances between the volcanoes, about 60 kilometers at most. And you have rapid ascent of magma through multiple pathways through the crust. So they've been studied relatively well before, but most of the work that's been done on the Galapagos has been looking at periods of eruption rather than interruptive periods. And they've been relatively consistent in what they found. There's kind of reliably or consistently found storage depths of about 5 kilometers beneath several of the volcanoes, deeper storage at some of the others. And what we found when we looked at the more recent data were that we were getting source depths that were relatively similar using similar modeling methods. What we can do now that we couldn't do before is look at the details of the time series progression of deformation. Because of these new consistent satellite missions from ESA, we've got reliable data that spans a decade, which at best has a 6-day separation and at worst kind of 12 to 24 days. So we looked at time series. These ones here are for caldera areas at the 6 different volcanoes. If you look at the cumulative displacement figure on the right, you can see huge numbers of fringes, an awful lot going on at all of them. Particularly if you note Sierra Negra, the scale here in millimeters is completely different from all of the others. It swamps it in terms of magnitude. And one of the first things that you notice when you look at these time series is that they appear to move together. And when you first spot this, you think, well, okay, so around this large eruption at Sierra Negra and around Fernandina in 2018, you have change points that occur more or less at the same time at several of the different volcanoes. And you also see that before the Wolf eruption in 2022. So Wolf, this is the one that actually erupted here, was uplifting and then started to subside after the eruption. But you also get a change in gradient of the displacement at Fernandina. You have a change at Darwin and at El Cedo and Serra Azul. So, this is something that people have pointed out before. I think it was initially suggested by Scott Baker during his PhD, but that was with much earlier data sets and it was looking at particular individual events. So we thought, well, we've got these time series, what we should do is really test if this is robust. Is it something that happens occasionally, or is it a kind of persistent feature of volcanism in the Galapagos? So we started off by looking at the timing of turning points, which for certain larger changes in trend, depending on the type of filtering you use, seem to line up. We did paired correlations between the different time series, which is consistent with what you kind of would think from looking at the time series by eye. You get episodes with increased positive correlation relative to the rest of the data set. And then we did temporal independent component analysis, which is breaking down a multivariate signal on the basis of maximizing the independence of the different components. If you're not familiar with that, this is a kind of a cartoon example. These are input signals that I mixed together. This is 3 kind of fairly random linear combinations of those inputs. And you can divide that out using principal component, which most people are quite similar with, in a way that does a really good job of maximizing the variance, the amount of the variance in the original signal that each component accounts for. Or you can do it on the basis of how independent they are, and that's normally done by the kurtosis or kind of peakedness of the signal. So you can use that for lots of different applications. So this is the kind of setup for spatial ICA, so trying to maximize the spatial independence of a set of interferograms. We did this over Lanzarote, which is where we take our undergrads in Leeds for their geophysics field training. And you can see over the Team and Fire lava fields here, you have nice subsidence patterns. And we used the ICA as a test as to whether these 2 patches of subsidence seem to be linked. Which they do. They appear in the same independent component. There's no reason to kind of separate them out, which is part of the reason that we think they're associated with lava flow subsidence rather than the contraction of something magmatic underneath. And the other argument is the kind of shape of them here. You see these features are associated with lava deltas. I mean, that's kind of unsurprising, except that these lava flows are 300 years old. So the fact that they're still subsiding feels like quite an impressive feat. So in the Galapagos, we applied this not spatially like that example, but temporally. So we divided the island up into with this higher sampling rate over the calderas than we did over the rest. So we got samples where most of the deformation was happening. And that gave us about 8,000 time series to play with. And then we clustered them to remove components that we thought were of significance. So this is an example of a component which seems to be active during this time window that I pointed out before. So that's the 2018 eruptions of Fernandina and Sierra Negra. And we would expect that component to have a strong weight. So this map here is essentially just giving you the weight of the component underneath at every individual pixel. If it was only active at this volcano, we should only see that volcano popping out in this image. But actually, we have a strong weighting for that component over at Sierra Negra, and we also see something at Wolf. During the Wolf eruption, which is this volcano up here, we also have strong signals in the calderas of Fernandina and Sierra Negra, which I think is a fairly robust piece of evidence that the processes that cause them are at least temporally correlated. So, there's a bunch of reasons you could come up with to explain this. So one is that there are correlations due to artifacts in the INSAR processing, perhaps to do with your choice of reference pixel, and that's something that we explored quite thoroughly and decided it couldn't really be the case. The other obvious thing is that there's static stress changes associated with some of the larger eruptions that are affecting the neighboring volcanoes. But if you look at particularly the Sierra Negra eruption and model what those Coulomb stress changes should be, they're just not of the magnitude that you'd expect to be making a difference at the neighboring volcanoes. The other possibility is shallow hydraulic connections between the volcanoes. But again, if that was the case, we'd really expect to see that geodetically, and we don't. You have clear space, clear water in between the deformation signals at each volcano. So I think the best explanation for this is that we have deeper connections between the magma supplies for the different volcanoes. So one of the obvious questions about this is whether this is something that's kind of uniformly happening in the Galapagos, or whether it happens during particular events. And to do this, we tried to estimate the time series of the intrusive flux into the Western Galapagos and compare that to the extrusive flux and see if perhaps during windows of high flux we had greater correlations. And to some extent you do see that over this period here. This is just high correlation count is just before the Sierra Negra and Fernandina eruptions, but it probably isn't the whole story. The majority of strong correlations between pairs of displacements that we see are positive. And you can kind of imagine a scenario as to why that would be the case, right? You have a kind of increased magma supply to various systems. You have simultaneous pressurization of the shallowest parts of those systems, assuming some good level of connectivity. in converse, if you have a lowering of the influx of melt into some of the systems, you might expect the magmas to go into a kind of cooling phase and both subside. So obviously a monotonic signal will always correlate with another monotonic signal. But what we see here is that these change together. And then negatively correlated displacements, which we do see in particular episodes in the Galapagos, seem to be very strongly correlated with shallow processes. So for example, the major eruptions at Sierra Negra introduced a phase of negatively correlated deformation at the different volcanoes. And I think one of the outstanding questions about this process is whether we have changes in the partitioning of melt between the different volcanic systems, or whether we're seeing differences which are associated with a driver which is shallower. So this is our kind of best guess at what's going on here. So we have no geodetic detection of lateral transfer, and we have pretty good geodetic evidence and also some petrological evidence for the location of the reservoirs in different parts of the Galapagos. There's good evidence for distinct kind of vertically extensive zones beneath the volcanoes through which magma is able to travel. So what we think is we have some layer which is sitting here at this sort of depth in an analogous way to what you see in Hawaii, what's been imaged in Hawaii seismically, and it's also been postulated in the Canary Islands, through which you have kind of some pore pressure stress transfer process. We don't think there's actually mass transfer between the volcanoes at this step. The composition of the material erupted from volcanoes is isotopically distinct, so that's not a plausible explanation. But you could kind of conceive of a zone through which you have some pore flow processes. So I think the questions that I'm still working on and interested in the Galapagos is how this interacts with the ring fault systems at the volcanoes, because that's certainly an amplifier to some of the deformation signals, which we don't really account for in our modeling. And also, what are the mechanisms for magma ascent? Do we have dikes that open and then contract, changing the flow rate? Do we have pathways for magma ascent that actually close off for a while, or is it relatively constant? And I think to answer that, you really need better temporal resolution of data than we currently have. Okay, so I think I'm going to leave it there. If anyone would like to discuss any of the case studies in more detail, I'd be really happy to afterwards. Thank you.